Hello and welcome to this live code hangout. I'm Briley and we're going to be working on some open source code today to do some remote sensing analysis on geospatial data. The goal of today's session, or the project, is to derive or obtain moisture stress index and leaf area index metrics, I suppose you would call them, based on some remote sensing data. And we'll need to go through some intermediary metrics, which may already be derived for us, in order to calculate the moisture stress index and leaf area index, depending on which modeling approach we take. Need some moisture stress index may be most straightforward. And we have these intermediary metrics actually that are useful for other derived metrics. So let's dig into the code. We're going to use a notebook interface called Marimo, or Marimo, I'm not sure how to pronounce that. The idea is that it's a reactive, batteries included, interactive notebook framework. It's inspired by Jupyter and Jupyter Lab and a few other projects that are prominent in the data science, Python data science community. The difference being everything is just Python, so that's going to give us a lot of benefits here. So what we'll do is we'll initialize a project. We'll create a branch. And we'll install Marimo. It has a project dependency. And we can see it has a few dependencies, but it's not massive. Markdown. YCRDT for real-time interactive, possibly multi-user interactivity. Interesting. YAML processing. Rough, good. Yeah, we have rough here. Starlet for serving. Uvicorn for hosting. WebSockets for real time. Cool. And then Click, I think, is a framework for interactive CLI. It's like CLI kit or something like that. H11. I'm not sure what a lot of these are, to be honest, but I recognize a few. All right, now I think we can try the Marimo tutorial intro real quick. So we're gonna activate this, and we're gonna try running Marimo tutorial intro. Just to take a look that everything is working. What that does is create some main pie for us. No, I'm sorry, this was actually the UV init that did this main pie. Misspoke. Edit intro pie in your browser. Okay. It's a has some, for me, somewhat familiar interface in terms of having cells. Created this in a very funny place, and it has widgets, interactive bits, and you can run or stop, interrupt, and then sell actions to move them around and things. Okay, it's mostly just Python underneath, but one thing I'm wondering why I did that. So I would like to just initialize a notebook. Let's go through the intro real quick. So you grab Marimo as Mo, and it can render some markdown here. So that's why we see this output of the cell here above the input. That's an interesting way of doing that. I suppose then you could hide the inputs. slider. I just realized my screen is not updated, so let me just really quickly fix this. Yeah, so here's our Marimo notebook. We're importing the code, and welcome to Marimo. And a slider, reactive Python notebook. So we have interestingly, so we define the slider and don't do anything with it, doesn't render it, but then we define a markdown cell, and we can include the slider in the markdown here. Interesting. And get the value multiplying this. So these are Python expressions inside the curly braces, very familiar to if you've worked with template languages. Try disabling automatic execution. All right. So, oh, cool. Yeah. So somehow you can show and hide that. I don't know how to get back to the hide. I guess it's just hide cell thing. One problem is that it's spilling off the top of the screen when I press that. So it's a small snag. Show code, so H. Hide code H. Okay, disable automatic execution. Marimo lets you disable automatic execution. Just go to notebook settings and set runtime on cell change to lazy. When the runtime is set lazy, after running a cell, Marimo marks its descendants as stale instead of automatically running them. The lazy runtime puts you in control over when the cells are run, while still giving guarantees about notebook state. This is interesting. That it's one of the selling points of Marimo, that the cells are reactive, so that if you change one, all the dependent cells like this, well, that's not a good example, but all the dependent cells will also change. Just go to the notebook settings. So there's some things over here. View files, explore variables, explore data sources, dependencies, packages, outline, chat with AI, live docs, notebook logs, tracing, snippets, secrets, scratchpad, feedback. Can have a little bit of a wider code. Interesting, custom CSS. Would have dark mode by chance? I'd appreciate that. Yes, wow. It's just much easier on the eyes, and I think a little more energy efficient. I don't know. I'm using large language models, and those are notoriously, I suppose, wasteful. Okay, and we can use UV for package management. Wow. And here's the on-cell change, lazy evaluation. Okay, good. On module change, AI. And I can bring my own API keys. Wow, this is super cool. Man. Okay, optional features, SQL cells, DuckDB, and SQL Glot. I don't know. Charts and data source view. Okay, it's going to use Altair. I like Altair. I haven't used it very much. Fast server-side charts. Vega, Fusion. Vega and Altair are kind of like pairs, like, as far as I remember. Altair's built on Vega or something like that. Rough for formatting. OpenAI for, I'll look at that in a bit. Export as IPy notebook, NB format. This is kind of nice. They're bridging the gap between the IPy notebook format and this Python-oriented format. And and they're promoting tests. Language server protocol, Python LSP, WebSockets. Wow. So I could give Claude, for example, access to this notebook running on a local WebSocket connection. Huh. Crazy. This is so nice. Enable experimental language server protocol support. You need Marimo LSP installed to use this. AI edit tooltip. Enable the experimental edit with AI tooltip and selecting code. Table charts enable experimental charting feature in tables. Data is saved in local storage, may not be performant. Wow. Okay, so this is very cool. So one problem is that at least it created this intro pie in some weird location. Let's continue going down really quick and then see what some of the UI components it has. It's just Python, easily versioned with Git, yielding minimal diffs. Legible for both humans and machines. Formatting using your tool of choice, rough. Usable as Python scripts. For it to launch my Firebot. You can run them as apps. Import them in other modules. Marimo command line tool. Marimo edits. Creating and editing notebooks using that. Alright, to start a Marimo notebook server. From there you can create a new notebook. And I suppose I do that right here. Add a file. How do I add a notebook? I don't know if there's some specific head matter or something like that. Marimo run notebook. Marimo convert IPy notebooks to Marimo apps. Wow. Marimo comes packaged with tutorials, data flow, more Marimo's automatic data flow. I'm gonna grab some tea while this Firebot's loading up. I'll be right back. Very cool. So let's continue. We're just going to go quickly through the capabilities of Marimo. Probably not through all these tutorials, but I will at another time work through those. Automatic execution, how to use UI elements, markdown. So this is really cool. They have built-in documentation. These tutorials are built into the editor. Really nice. And different layouts, app view. Command palette, man, this is just very advanced software. In addition to tutorials, we have our examples in the GitHub repo. The editor, you can save, run, console output. Finally, fun fact, the name Marimo is reference to a type of algae that, under the right conditions, clumps together to form a small sphere called Marimo moss ball. Made of just thousands of algae, these beloved assemblages are greater than the sum of their parts. Huh. What? Seriously? Cloud of Foro ball. Wow. Kind of cool. How do you pronounce it though? Interesting. Future of intelligence on Earth. Intelligent life, they're just waiting their turn. Confection. All right, that's an interesting aside. So if I want to create a file, I guess just when I open it, what happens? Okay, so it's just a standard Python file. How do I create same a notebook? One thing I'm wondering also, does it have Git integration built in? That's not a deal breaker, of course. It's not even a big deal. It has a terminal built in, so there I can do my Git commands. That's fine then. Okay. So what is the difference between a Python file and a Marimo notebook? That's what I'm... Quick start. We've installed Marimo. Marimo edit. Create or edit notebooks with that. All right. So it's running. I suppose I should just use the Marimo user interface to the extent possible. Is there a shortcut command for this? Terminal. Ah, interesting. So it takes me to sort of a landing page. What I did is I just ran the tutorial last time, Marimo tutorial intro, which may be just a static file. Now, if I run Marimo edit, here we go. Create a new notebook. Untitled Marimo app. So I'm gonna hop over to VS Code real quick. We'll go ahead and commit these. It's a pretty young project, version 13 as of today's live stream. What I need to do is actually stage this, then generate the thing. Commit that. Save notebook as. Alright, so this is that notebook.py. Save as. Yeah, now what does this look like? Well, we can open it. It's just Python. App cell with decorator pattern. Oh, wow. This is super cool. Generate with AI. Okay, so now we have a development tool, but I'd like to take a step back before diving into the code and take a look at the project requirements. So see, can I just open that here? So it opens in the sidebar. So let's go ahead and switch back to VS Code real quick. Open in preview. So our project requirements, we want to derive or obtain the moisture stress index and leaf area index. I use those derive or obtain because we may be able to just download a dataset that already has that. So I think if we formulate a research question, I can use perplexity, for example. And I'll bring this over here. 2 remote sensing metrics: moisture stress index, leaf area index. So I have a project with the goal of deriving or obtaining 2 remote sensing metrics: moisture stress index and leaf area index. Where possible, I would like to use open data sources, and open source libraries. If it exists, I would prefer to use data sources that have already derived those metrics, or at the very least, open source Python libraries that can take existing remote sensing data sources, download the appropriate data, and derive the results with a high level of abstraction. This is a research task, and I think we'll kind of want to do some academic-oriented research as well as web. I'm not sure if social research would be relevant here. It might burn through some of the credits. So I'm going to take this prompt and actually hop over to Claude, where I've started sketching out this idea. So as you know, I'm prompting generative AI research assistant Perplexity AI to help me kick this project off by identifying any off-the-shelf components or data that may more quickly help me arrive at the goal. Below is my current research prompt. Please enhance the prompt to help the research agent be more effective at arriving at the right data and sources so I can build this project more efficiently. This is just called meta prompting. I'm using large language model to help me basically explain better to another large language model what I'm trying to do. You know, this could also be used when explaining the task to a person. You know, these type of communication skills are interchangeable with large language models and collaborating with people. So I think in any case, communication is one of our most useful skill sets to develop. So here's the advanced or augmented prompt. I'm starting a geospatial analysis project focused on vegetation and moisture metrics with these specific goals. Obtain or derive moisture stress index, MSI equals NI, or near infrared, and SWIR, SWIR. Another type of data channel, and obtain or derive a leaf area index, which there isn't necessarily a clear specification for that, I guess. Please help me identify pre-computed data products, specifically LAI products from NASA, MODIS, VIRS, Copernicus Global Land Service, or other providers, any existing MSI data products or services that directly provide this metric. Resolution and temporal coverage requirements. Prefer 10 to 30 meter resolution global coverage with the data from 2020 to present. This is already much better than my prompt. Even specifying like common open data sources. Copernicus is, I think, part of the European Union space program, ESA. And then we have NASA, National Aeronautics and Space Administration. Python libraries and frameworks that can download and process satellite imagery, e.g. Google Earth Engine, Python API, X-Array, or RIOX, or Array. I think I did find something around that area, because we're going to want to run these locally. Calculate these indices efficiently. Specific functions in GDAL, Geodata Abstraction Library, Raster.io. It's another way of working with these. Essentially, remote sensing images that are like matrices or pixel kind. You could think of it pixel data, because there's essentially images but different sensors that are out of even the visual range. Or specialized Earth observation libraries. Provide high-level abstractions for deriving these metrics from raw satellite data. I don't want to really kind of be working too close to the metal, so to speak, like working with vector operations and things and mathematical operations. It's not my sort of skill set or wheelhouse to the extent possible. There are people who are much more skilled at that, and I'd like to use their work in an abstract form because they'll have gone through so many details and iterations. This is my general philosophy when I'm developing things. There's just a lot of experience and knowledge in the community, and if you can build on mature solutions that have been around a while, and I've had a lot of contributors, even at bringing small pieces of that together, you're just better off in the long run. So avoid this not invented here syndrome, because I'm far from the smartest person in the room, and nobody really has that title. We're all smart in our own different ways. All right. And in tutorials or code examples demonstrating these, that's super helpful. So we could, also pass this into the large language model for assistance as well, because it has a lot of this tacit knowledge. For implementing, please identify which satellite platforms are most appropriate. I think Sentinel-2, I'm leaning towards that. I don't know. Specific bands needed for each metric. So they're multi-sensor arrays with different sensors on the satellite, and then they combine those into images that have different bands. Like near infrared band was one that I mentioned earlier. Any pre-processing steps required? Atmospheric correction. This is another one. I just hope that we can get this directly from the data provider. It's complex stuff, really complex. Computational considerations for large-scale processing. I'm running this on a laptop. We don't want to have heavy computation, so if the data is already derived, that's much better for our needs. My preferences for open data sources and open source tools with strong documentation and active communities. I'm proficient in Python and have experience with basic GIS concepts. Geographic information systems, or sciences, depending how you say it, or your perspective is, but would benefit from tools that abstract away some of the complexity of remote sensing. It's nuts, it's crazy, interesting, but yeah, there's a lot of people who are really deep into that. So now I have a much better prompt. Boom. Let's pass that to complexity research. Let it break down the research problem. And in parallel, I'm going to hop over here to my little Google workspace and run Gemini with the same prompt. Gemini also has this deep research mode. Took out all the formatting there, but this right here, Gemini deep research with 2.5 Pro. Let's see what kind of result we can get here. So what they both do, Gemini and Perplexity, they save you a lot of time. We should always kind of step back before diving straight into the code. We should step back and get an idea of what the project is, think about it a little bit, and research if possible. What are the ingredients, the frameworks and libraries I'm going to use to build this? What are the goals of the project? I don't have a lot in terms of goals beyond computing these two metrics. So then I could end up doing this research or use the agents to help me save that time. So they're going to look across different websites. They're breaking down the task, and this is a complex task. So actually, it would not surprise me if these research steps do take a considerable amount of time. But so what it's doing is it's identified multiple searches will be initiated to cover all aspects of the query comprehensively. So this is already a big thing. It helped confirm the availability of the resolutions of data and remote sensing ground truth validation. This is nuts. Okay, let's just take a look at the plan here. So it has my big prompt: identify pre-computed leaf area index data products. Start with that. Is it already existing? If so, check that box. Search for existing moisture stress index. So it knows right away just to see if we have those. Any open source Python libraries suitable for accessing and downloading processing satellite imagery relevant to these two calculations: leaf area index and moisture stress index. Identify specific open source Python libraries and locate tutorials and examples. So it's kind of breaking it down in order. So we'll start the research there. I should have started them in the same time, but let's just say I started them 2 minutes apart. And this deep research capability is available in other of these large language model products. Claude is launching a deep research feature in their newly announced kind of upper tier. I think it's 100 euros or 200 a month, euros or dollars a month. But it should be coming into their more mainstream subscriptions soon. In the meantime, Perplexity and Gemini have this. The interesting thing, if you want to save a little bit, you can actually use Perplexity for free, and it will give you a deep research query, up to 3 pro queries a day. And I don't know how they, how intensively it'll search, depending on the free one. But the amount of time it saves, I think these start to justify a little bit of a subscription monthly cost if you have the means, because it can save you 30 minutes, 60 minutes, hours, depending on the type of work you're doing, and get you closer to your goals. Now, that said, Perplexity is around 20 euros a month if you do go the subscription route. But Google has this thing, you can do their Google Gemini Advanced, it's around 22 a month. Or you can set up what's called Google Workspace, and it's sort of like oriented towards businesses who have a lot of employees and collaborate on documentation and research and projects and things. So it has like Google Mail or Gmail, Google Drive and all those products, but also it includes the Gemini Advanced. And this is interesting because even though I'm not an organization, the Workspace's pricing is 16 a month per user, 16 euros a month per user. And so it's already, about 5 euros cheaper per month than if I were to just subscribe to Gemini Advanced. And I'm the only user there on my Google Workspace. It's a bit of overkill. I don't know the half of what's going on in the Workspace's admin section. There's quite a lot to it, but with about 30 minutes to an hour, I was able to set up a domain name and things like that and get rolling. And now I'm just using all the Google tools with Gemini integrated, including this deep research, which then I can send to Google Drive. All right, so we have some results. I'm not going to read all these off, but you can see it's gathered information, and now I need to think about the language, or queries in English. So it's breaking down the problem step by step, how to respond here. Asking help with geospatial analysis product, specifically these MSI and LAI. Metrics, pre-computed data products. Pre-computed data products. LAI and Modus. LAI, interesting. So the nice thing about these research agents is not only do they go out and search for you, but they bring back the sources. It's amazing. The level 4 Modus Global Leaf Index and fraction of photosynthetically active radiation, FPR. Fraction of photosynthetically active radiation. I guess it's that showing how much light is radiated or emitted back without the photosynthetic bands. 8-day, 500 meter resolution on a sinusoidal grid. Science data sets provided in the Modus. Earth data, NASA. The problem is, well, not a problem currently, but it's a problem we face, is that this data is volatile and possibly could be yanked, and these agencies could be defunded, and privatization. There's a big privatization thrust, particularly in the United States. Hey, Boskans, welcome to the chat. How you doing today? So I just don't have a lot of trust that this data from NASA will be available. Or it's not that I don't trust it, but I just have some uncertainty there. Nonetheless, if it works, if it's available, and there will be some lag to it, because especially with derived data, but it does look like they cut it off at a certain point. So there's other reasons for the data to not be available. Sometimes they'll come up with a new metric and they'll stop computing the old metrics, for example. Some of this is funding dependent, or there's a particular study that was going on that may or may not be active any longer. So yeah, we'll come back to these specific findings. I was just kind of illustrating here that it also gives me footnotes and quite a lot of you could sort of speak thought or consideration going into how to respond. And it's writing a research report. That's the end goal. The UI might be glitching a bit here, but let's see. So it looks like Gemini Advanced did return a result a little bit sooner. And I'll post this in the GitHub repository. So all of this that I'm working on today is open source. Deriving high-resolution vegetation metrics, LAI and MSI, using open-source geospatial tools. So I have a research report written by Gemini Advanced. Project context. This report provides guidance for a geospatial analysis project focused on obtaining or deriving two critical vegetation metrics, leaf area index and moisture stress index. The specific objectives are to achieve global coverage at a spatial resolution of 10 to 30 meters for the period of 2020 to present. A central requirement is utilization of open data sources and open source Python tools. Leveraging existing proficiency in Python and foundational geographic information system concepts while seeking methods that abstract some of the inherent complexities of remote sensing data processing. So it breaks down leaf area index and moisture stress index are fundamental variables in monitoring and understanding terrestrial ecosystems. Leaf area index, defined as the one-sided green leaf area per ground unit area, is a key indicator of canopy structure, vegetation density, and potential photosynthetic activity. It plays a crucial role in models simulating vegetation productivity, carbon cycles, and energy exchange between the land surface and atmosphere. All right. Yes, we have moisture stress index, typically calculated as the ratio of near infrared (NIR) and shortwave infrared (SWIR) reflectance. MSI equals. So these come directly out of the satellite imagery, and it's just vector operation across those two channels, I suppose. So that's cool. It is primarily sensitive to the amount of water held within vegetation canopies. As leaves experience water stress, the reflectance in this shortwave infrared region increases relative to the near infrared region, causing the moisture stress index value to decrease. This makes moisture stress index a valuable tool for monitoring vegetation water content, assessing drought impacts, and supporting agricultural water management. This is pretty cool. I did live for a few years in California and grew up in Kansas. About half of my childhood was in Kansas. And so the agricultural water management has come across my radar a few times, particularly in California, where there's a lot of drought preparedness, and they had this Nevada irrigation district that brought these channels of water all throughout the region in this hilly terrain. They had these just channels of water. They were always flowing there, and you'd have a certain amount of that water that you were able to use for your crop. Very interesting. I should actually reach out to my friend John, who actually worked for the municipality Water Management District. See what he says about this project. The report systematically addresses the product's requirements. It begins evaluating pre-computed global leaf area index data and comparing the specifications against project needs. Yeah, the project specs about the resolution may not be correct. Subsequently, the report addresses the availability of pre-computed moisture sensitivity index and details. Review of pre-computed global LAI products. A primary objective is to obtain readily available pre-computed leaf area index datasets to 10 to 30 meter resolution. That's maybe, I think maybe reasonable. The global requirement is not the case, but I can't say much more about the specific areas of interest. Several established global leaf area index projects exist, but their specifications must be carefully examined. NASA MODIS, Moderate Resolution Imaging Spectroradiometer, MODIS, LAI FPIR Index Collection 6.1, provides globally consistent LAI estimates. It's generated using radiative transfer model inversion algorithm. This is what I'm talking about. This is crazy stuff. However, its spatial resolution is 500 meters. That's cool. That's cool. And it's provided as an 8-day composite product. Yeah. So, yeah, this makes sense. You have to quantize and data resolution. 500 meters is actually pretty dang good for certain use cases, or kind of like larger, mid to large scale planning, resource allocation. So NASA reviews. Okay, so here we have a table. This is great. And they're looking about 300, 500 meter, 8-day composite, 10-day composite, 2. And so that's great. See, it summarizes the whole thing in a table. I love it. Given the lack of suitable pre-computed products, and the 10 to 30 meter resolution requires processing imagery from appropriate satellite sensors. So we could break down this project in a couple of segments. First, I would say, how do we obtain the existing Copernicus data? Just start there, and then we can worry about, do we need the data at 10 to 30 meters, or is that an excessive requirement? What's the goal of the analysis? The underlying principle is that denser, healthier vegetation reflects more near-infrared light and absorbs more red light, leading to higher NDVI values, which generally correlate with higher leaf area index. The relationship can be expressed as so. So here we have satellite platforms for the 10 to 30 meter. And suitability. So yeah, we don't have to read the whole thing. I'm going to generate an audio overview. This is fun. It should take a little bit of time. In the meantime, let's export this, copy the contents, and let's see if it copied as a markdown format or how we got this. Not quite. All right. So if I export, this is a bit challenging. Let me refresh here. See if we got a report. So it's writing it still. I think Perplexity got choked up a bit, unfortunately. So I'll export this to docs. We'll get a document here. Download. Markdown. Yeah. There we go. Where's the download though? And there it goes. I just had to convert that, took a little bit. So we'll go ahead and remote sensing analysis. Let's research, replace it. Now if we hop back over, don't save that, and there we go. Very cool. One thing that's a bit annoying is it does these section numbers. And it defaults to page format, which okay. If I change the requirements, we did find suitable pre-computed. Just wait a little bit longer while it prepares the export. So I'd say in this research, Jim and I kind of won, and as a bonus, we get this decoding Earth's green. Here we go. Save this. Research. We get a audio overview. Let's take a listen. It's 8 minutes. We don't have to listen to the whole thing, but maybe it'll be interesting.
Welcome to the Deep Dive. Today we're digging into global vegetation mapping.
That's right.
You wanted to look at getting a really detailed view, like 10 to 30 meters from 2020 onwards.
Yeah, using open data, Python tools. Focusing on leaf area index, LAI, and the moisture stress index, MSI.
Okay, 2 key metrics. So our mission here is to see what the sources say about, well, whether that's actually feasible.
Exactly, and why these metrics matter. LAI, that's the leaf area index. It's basically how much green leaf area you have per unit of ground. Super important for understanding, canopy density, photosynthesis potential.
So like the plant's engine size.
Kind of, yeah. It feeds into models for productivity, carbon cycles, all that good stuff.
MSI.
Moisture stress, right, MSI. That one uses near-infrared, NIR, and shortwave infrared, SWIRE light.
Okay.
Healthy, well-watered plants absorb a lot of SWIRE. When they get stressed, water stress, they reflect more SWIRE. So the MSI value, which is NIR divided by SWIRE, goes down.
Okay. So lower MSI means stressed plants, like a
Yeah.
remote drought detector.
Pretty much. Really useful for agriculture, drought monitoring.
Got it. So the source material looked at what existing products first.
Yeah, first checking if you can just, download this stuff ready-made, then how to actually derive LAI and MSI if not.
And the satellites, the tools.
Satellites, bands, Python libraries, processing steps, and crucially, validation.
Okay, let's jump in. The big question first. Can we just download a global 1030-meter LAI map for the last few years?
The short answer seems to be no.
No. Okay.
There are global LAI products out there, like from NASA's MODIS and VIARS, or the Copernicus CGLS service.
Well,
But they're at coarser resolutions. We're talking 300 meters, 500 meters, not the 10 to 30 you're after.
so if you want that detail, you have to make it yourself. Derive it.
That's the conclusion, yeah.
Right.
Which leads to how you derive it.
Right. And the sources mention NDVI, Normalized Difference Vegetation Index.
Yep, that's a common starting point. It uses the red and near-infrared bands. You know the formula, NIR red. NIR plus red.
Because healthy plants absorb red light and reflect NIR.
Exactly. So higher NDVI often correlates with higher LAI. It's intuitive.
But not perfect, I gather.
Definitely not. The sources flag limitations. Big one is saturation.
Saturation.
Yeah, in really dense vegetation, like a thick forest canopy, adding more leaves doesn't really increase the NDVI much more. It sort of hits a ceiling.
Okay. So the relationship breaks down.
Right. And the relationship between NDVI and LAI isn't universal. It changes depending on the type of vegetation, the region. You really need specific calibration.
So using NDVI is accessible, but you need to be careful about its accuracy. What about other methods? RTMs?
Radio transfer models. Yeah, that's the more physics-based approach.
Sounds complex.
It is. They simulate how sunlight interacts with the whole canopy structure.
Yeah.
You can invert these models using satellite data to estimate LAI. Potentially more accurate.
But computationally heavy.
Much more demanding, yeah. So for getting started, maybe those NDVI relationships are more practical, just keeping the limitations in mind.
Okay, what about MSI? Is that something you calculate or download?
For MSI at this resolution, the sources point towards calculation. There aren't really standard pre-computed global products like there are for LAI, even at coarser scales.
So you calculate it from the satellite bands directly.
Yep. The formula's simpler too, just DEN-IR reflectance divided by SWIRE reflectance. Specifically the SWIRE band, around 1.6 micrometers.
Because healthy leaves absorb that SWIRE due to water.
Exactly. Less water, more SWIRE reflection, lower MSI.
But again, caveats.
Always. Other things can influence MSI, like the canopy structure itself, how much soil you see through the leaves, even atmospheric effects, although surface reflectance helps with that last one, so interpretation needs care.
Right, okay. Satellites.
Huh.
Which ones have the right bands, the right resolution?
Sentinel-2 looks like the prime candidate here.
Why Sentinel-2?
It gives you that 10-meter resolution for red and NIR, and 20 meters for the key SWIRE band. Plus, it revisits frequently.
10 and 20 meters, that fits the goal.
Any others?
Landsat 8 and 9 are great alternatives. They provide all of the necessary bands at 30-meter resolution.
A bit coarser, but still good. Yeah, and Landsat has that amazing long historical archive. Crucially, both Sentinel-2 and Landsat provide surface reflectance products.
Meaning the atmospheric interference is already corrected for.
Largely, yes. It saves a huge amount of complex pre-processing. You want to work with surface reflectance for these kinds of index calculations.
Makes sense. Okay, data sources sorted. How about processing all this? Python.
Absolutely. The open source Python world is brilliant for this.
Like what specifically?
Well, a big one mentioned is Google Earth Engine, GEE.
I've heard of that. Cloud-based.
Totally. It has vast archives of satellite data, including Sentinel-2 and Landsat SR right there. And it lets you run the analysis on Google servers.
So it handles the massive data volumes and computation.
Exactly. For global or large area analysis, it can be a real game changer. Avoids downloading terabytes of data.
But what if you want more control or need to run it locally?
Then you've got libraries like Stack for finding and managing data, and Zarya with Reoxarray for handling the geospatial raster data itself, often in efficient formats like cloud-optimized geotiffs.
And for scaling up calculations.
Dask is great for parallel processing, speeding things up if you're using your own machine or cluster.
Any specific libraries for the indices themselves?
Yeah, Spindex is mentioned. It's a neat library that has pre-built functions for calculating MSI, NDVI, and tons of other geospatial indices. Saves you coding the formulas manually.
Nice. So putting it together,
Yeah?
a workflow could be grab Sentinel-2 or Landsat surface reflectance.
Yep.
Use the quality bands they provide to mask out clouds and shadows.
It's an essential step.
Calculate MSI using NIR and SWIRE, maybe resampling Sentinel-2's NIR to match the SWIRE resolution.
Good point. Yeah, you'd need the bands at the same resolution for the calculation, so resampling the 10 meter NIR to 20 meters might be needed for MSI with Sentinel-2.
Okay, and then derive LAI, probably from NDVI,
Yeah.
using some kind of calibrated function for your area of interest.
That captures the core process. But don't forget the final step.
Which is?
Validation. You can't just make the maps. You need to know how good they are.
Right. How do you validate something like this on a global scale?
It's tough. Ideally, you compare with ground measurements, but those are sparse. You can also compare with other trusted, maybe coarser data sets, or just analyze if the patterns make sense. Does MSI drop during a known drought? Does LAI follow expected seasonal patterns?
Okay, so it requires some critical assessment.
Definitely.
All right, summing up then. It seems like getting a ready-made, off-the-shelf global LAI map at that super high 1030-meter resolution isn't currently a thing.
Correct. And MSI needs to be calculated.
But the combination of high-res data, especially Sentinel-2 and Landsat, plus these powerful Python tools, particularly something like Google Earth Engine, it seems like driving these indices globally is achievable.
It looks very feasible, yes. The pathway is there.
The main hurdles being getting the LAI derivation right for different places.
Yeah, that NDVI-LAI relationship calibration.
And doing robust validation for both LAI and MSI.
Those are the key challenges highlighted.
Okay, well, the ability to generate this kind of detailed vegetation information
Yeah.
globally is pretty exciting. It opens up a lot of possibilities for environmental monitoring, doesn't it?
For sure, agriculture, ecosystems, climate change impacts.
So, a final thought for our listeners. With this potential to map global vegetation health in such detail, what specific ecological or agricultural questions could you start exploring? Thanks for this deep dive.
My pleasure.
Yeah, it's pretty cool. It kind of makes it more accessible too. I'm gonna go ahead and save this with the repo. Podcast. And we have another research task going on here for a tutorial. Essentially, let's start an analysis using the existing data sources. While this is generating and researching for us, I'm going to go ahead and take a break. Just to summarize, this is ideally we won't have to do the computationally heavy and protracted work of generating or developing these geospatial pipelines and understanding the algorithms and assembling the libraries if the existing data suits the needs of the project. So naturally we want to start there. Let's get a tutorial to help us get the data from the existing sources. Okay, I'll be back in a little while. Okay, it's still working on our analysis here. Maybe it's having a bit of troubles. Nonetheless. Oh, looks like we got it. Step-by-step tutorial. Google Earth Engine requires users to authenticate their access. Grab a bounding box. Bounding box is fine. Visualizing it. Use the matplotlib. Modus via Google Earth Engine. Planetary Scale Platform for Earth Science, Data and Analysis. Nice. This is what I'm talking about. Impact. Scientific and humanitarian impact. This is the important. This is the type of impact we should be focused on. In addition to business impact. Nonprofit organizations, academic and educational, government activity. Okay. Probably didn't need to enable. Because this requires quite a lot. Google Cloud Console. I don't want to go all in on this. This heavy requirements for this project. I want it more simple. Start researching that. All right, so we're just over an hour in. All right, I'll leave this off stream. And I'll go ahead and close Perplexity. It kind of got stuck there. And we'll start to develop a little bit here. Interesting. It's a big web file. I don't know. YouTube's gonna appreciate that. Let's give it a try. So, yeah, it would be nice if the notebooks would appear over here so I could switch between them. I don't know how you're supposed to navigate in a project with multiple notebooks. It's confusing. It's got a scratch pad, it's cool. Live docs, yeah. Interesting, that's cool. All right. Let's create a work plan for creating a Python notebook using Marimo, installing necessary dependencies using UV, and downloading the pre-computed data products from publicly available open data sources, i.e. without commercial restrictions or prohibitive access controls. So we have UV, we've installed. It's going with Earth Engine API as well, isn't it? This is the problem. You have to register for commercial use and pay a pricing plan $500 a month for basic access. Okay. All right. From Modus LAI, NASA Earth data completely free, requires simple account registration. Azure Open Data Sets, free tier available. Google Cloud, public data sets for single tuner. Copernicus, yeah, there we are, Open Data Hub. Interesting. This is tricky. All right, so we'll copy this README. Markdown lint, manual markdown lint. we see more accurately what's changed. If I look here, README, and I did change the remote sensing. So essentially what changed, data sources were added. NASA Earth data, Copernicus. And honestly, I think I'll remove these. It's just a bit of noise and confusing the goal. We have these two goals, MSI and LAI. And DVI. So it may be that it's enhanced vegetation index. Could be the basis of the leaf area index. And NDVI or other vegetation indexes. Back. Normalized difference. Water index, soil index, vegetation condition index. Normalized vegetation vigor relative to historical data. Yeah, so we're not going to probably go that deep. Alright, so just kind of simplifying our README, keep our focus on primary goal metrics. Yes. Whew. Nice, we're looking good. Okay. So the work plan hit a limit. It's quite a lot. I was writing the Python code for me. Where are we at? 1.5 hours. So let's spend about 30 more minutes here. And write some code. There's quite a lot of pre-planning and research. This is a complicated task, though. NASA Earth data credentials. I've got these imports, which shouldn't actually work unless we install those, I think, right? So if I run that, run this, okay. I'll already interface in the RC files. These are probably the standard libraries. Okay, so the OS is standard library. I guess netrc is standard library. Netrc file. What is the netrc file? Interesting. It returns. Huh. So that's working. Why isn't this working? Home directory. I just want to disable it on this. So I need to set up our model context provider. MCP.json, I think it is. select that one. So, whoops, give our notebook. And then we're going to add the context. Resolve library ID. Hopefully it'll run that without having to specify. Resolve library ID. With the name, library name Marimo. Got it. And now we're going to get the docs for that. So we'll have the latest documentation for Marimo built basically 2 days ago. Wait, is it in NetRC? Is there a different approach there? Text UI, password. We have a little bit of issue. Undefined name Mo. So it's a bit of an awkward developer experience. Going back and forth. We're using all right. Yeah, there's a notebook there. So how do I refresh? Just refresh the page, I guess. Restart the session. So that's not a great experience. Straight out of the box, we're having a bit of troubles. I think you have to display them in Markdown. Just see if I can manually download the data. So yeah, how do we use an interactive element? You define it, and then you. Oh, okay. So it looks like the last element needs to be this. Cell wasn't run before it has errors. Cell defines variables from other cells. Why can't I redefine variables? Let me just try this. It might be that I don't need to. Let's just see if we can get these to display. I thought I disabled Grammarly, man. So we have that and password input. Okay. Run this. Oh, okay. Oh, yeah, that's the key difference. So you have to have it as the last line. It's like the return. Run that. All right, so there we go. Good grief. We started. Now we're making progress. Huh. All right, and in the meantime, I am downloading QGIS. A lot of times it's just a good tool to start shaping these kind of geospatial analyses with, and I haven't reused it in a while, so it's good to get it back on my computer. I'm going to take a quick break. I'll be right back. Okay, there's layers of learning here. Haven't been doing geospatial in a while. Very cool. So I could, in fact, the last expression of a cell is its visual output, rendered above the cell. Outputs are included in the app or read-only view of the notebook. Marimo comes out of the box with a number of elements to help you make rich outputs, documented in the API reference. Markdown is written here, and you can include these UI elements in the Markdown. This is cool. So I think one thing I can do is define these. Sort of do a nice. It's like QGIS has been around enough. Why can't they notarize the installation? I'm complaining a lot, but it's a relatively big organization. Granted, this is Apple's sort of, in a way, fault for requiring this, but under the privacy and security, I just have to tell it to allow QGIS to open anyway. Alright, so we got some progress here. Earth data credentials. Okay, we've got QGIS 4.0 coming soon. Nice. Migrating Qt 6 and QGIS 4 October 2025. Modern libraries with performance and security improvements, a smooth transition for plugin devs, and a few pleasant surprises. Very cool. So we're essentially Modis. So I'm just trying to think the whole thing through. We need a script to download the data, and it would be nice to have a visual interface to explore it. So that's why the notebook interface is natural. We're not set on using this. We can use Jupyter Lab, for example. Sentinel-2 image downloader. And that's probably under the web, no? raster, plugins, Sentinel-2, image downloader. Okay. Hmm. $16,000 downloads versus 104,000 downloads. This plugin allows users to download the Sentinel-2 satellite image from Google Earth Engine into QGIS. Sentinel Hub. Plugin enables users to harness the power of Sentinel Hub service directly from QGIS. The plugin allows you to directly access Copernicus satellite imagery in QGIS, enabling exploration, customization, and image download. A lot of downloads for this plugin, but it may not work in macOS. Trial account. Crap. So the first challenge with this is just getting the data. Copernicus browser. Complete archive, Sentinel 1, 2, 3, 5P6. Wow. Central hub for accessing, exploring, and utilizing the wealth of Earth observation and environmental data provided by these Sentinel missions. You simply go to the area of interest, select the data sources, time range, and cloud coverage, and inspect the resulting data. You can continue the tutorial by clicking there. Wow. Access with limited functionality. To be able to use all of the functions, you need a free account. Logged in users can use their custom themes, save and load pins, measure distances, create a time lapse, and use extended image download. All right, I think I'll need to register for this. This is nice. Just getting the data. I don't need to actually do that in Python. At this point, just to start working with it. So, I'm going to go to the area of interest. Finland. I guess any area is fine. Let's start with Hämeenlinna. It's like it's not computed for that date. Strange. There's a big band. Several bands where it's not computed. 30% coverage, I guess. So you have to combine multiple days. But here's one where it's available. A little bit cloudy. That's another problem in Finland. Dimensionless index measuring the one-sided green leaf area over a unit of land. Implementing snap without input and output validation. So it needs all of these bands. All right. So now we have the Earth engine. Just out of curiosity, Gulf of America. Douchebags. So it makes sense. It can't quite calculate this in urban areas, so it's going to have gaps around there. Let's just say we want this data. can't beat that. We're ready to roll. So your lab is much more complicated. So we need GMAP and EE. Let's see if there's requirements text here. The README. So okay, it's already there. So now we have this Jupyter Lab, GMAP. We'll bring in dependencies. Just run straight into code. Log is kind of missing some key steps. Let's just see if this works. So we should be fine with 312. Okay, please authorize the authenticate. Any authenticate? Let's just try this. Okay. Try to get this data for Finland, or yeah. Hmm. Three years ago. Yeah, it's not printing. Boy. we're about 2.5 hours in. Got mixed results. We have some good plans, but not much in terms of action and outcomes. For some reason, this map isn't rendering. Maybe we're pretty close, but for whatever reason... there we are. We rendered that time. Okay. So we do have a leaf area index for Finland. Hey, I'm glad for that. It's spotty at best. I need to take a break and reevaluate this project. But I think so. We do have progress. We were able to complete and calculate the leaf area index. I can clean up this code, cite the source. Now, its utility would depend on the project. And we would need to describe how to interpret the data, and it might be also good to have some opacity here so we can see why there are some gaps. For example, Landsat or something could show us areas that aren't forested, and lakes, of course. All right, well, my name is Briley. This has been another Live Code Hangout where we've explored some geospatial data, made a bit of progress on an interesting task. I hope you're doing well, and if you like to try this code out, I'll make sure to push this to GitHub. Have a great day.